Okay, our next section is going to be on the bipolar transistor, which is one of the two main types of transistors that's used widely in electronics. And these transistors consist of two p-n junctions which are close together, such that the current through one affects the current through the other, just as it says here. In fact, what happens is that the current between the emitter and base electrodes, one of the p-n junctions, affects the output current, which we call the collector current. And in fact, you've got the device can therefore act as a switch or in a transistor, or it can act as an amplifier. These are components themselves, which you find in all circuits or many circuits in very large numbers. So you can have a circuit made up of purely bipolar transistors, or you can combine them with MOSFET transistors for additional functionality. So you can have the two different types of transistors being fabricated on the same chip together. Now, the first transistors, the bipolar transistors, were made from germanium, but nowadays most are made from silicon, which, as I told you at the start, is the most widely used semiconductor. But you can also use other semiconductors for bipolar transistors as well. For example, gallium arsenide and silicon germanium. These are widely used in heterojunction bipolar transistors, whereby you're using band engineering and also the different materials to obtain different and higher mobilities to get advanced performance. So we're covering the most basic operation of the bipolar transistors, but it goes from different materials to different band gaps to, several different types of materials on the same semiconductor substrate in order to achieve higher performance. And I have provided some notes for you on that, which might be interesting when you cover this section or complete this section. But for our purposes, we're really going to just look at the basic functionality. And that is to say that understand how these two diodes, you can see one there and one there, how these two p-n diodes achieve the amplifying and switching operation. Well, there's two main types that you can get, two main types of bipolar transistor that you can get. One is a PNP transistor, which is this first one at the top, and it's called a PNP because there's a base, an emitter, a base, and collector, which have the doping level of p-type in the emitter and base, and n-type in the, it has p-type in the emitter and collector, and n-type in the base region, which is in between the emitter and collector. And we also have an n-type, which we call an NPN transistor. And this is the one that we're going to concentrate on in this course because it gives you the higher performance on the whole. And in the n-type, we have the emitter here and collector being doped n-type, where the majority carriers are electrons. And in between those is a small base region, which is doped p-type. In other words, the majority carrier is of holes. So in both these cases, as you can see, there's three terminals, as they're known, this emitter, the base, and collector. And they're three different regions. It looks like they're symmetrical, but in fact they're not, and that's quite important. So if you just go down here to the NPN type, you can see that there's a plus for the emitter, it's N plus, whereas the collector is just doped N. And the plus means that there's more doping in the emitter compared with the collector. And we'll see that that has a very large effect on how the device is operating. So the collector is low doped, it could even be N minus. The base is in the middle. It's got a moderate doping, and we're going to see how the doping levels will affect the output characteristic. So if we just focus on the NPN, well, either case, in fact, normally the devices are they can operate with different voltages applied to each of the junctions and have different benefits, but we normally talk about these bipolars being in forward active mode, whereby the emitter base junction is forward bias and the collector base junction between the collector and base region is reverse bias. So you can see that on this schematic here of the NPN, that's their common mode. And you've got this first junction here is forward bias, the second junction VBC as it's known is in reverse bias. On the right-hand side here are the circuit symbols or the circuit diagrams for the transistors. And you can see that there's an emitter here, a base and collector. And we show the conventional current flow as going from the emitter through to the collector. Okay, that's the conventional current is highlighted with the arrows here, the collector through the base and into the emitter. But in the case of an NPN transistor, we're talking about the electron flow, which you have to remember is in the opposite direction to the conventional current. So in fact, the electrons will be flowing from the emitter through the base and into the collector. In fact, what happens is that there's a very small current flow between the base and emitter, and you can see that's called the base current, and this very small current that goes from that first junction results in a much larger current flow through to the collector, and that's how the device is going to operate as a switch. But what we need to notice is that this first junction is forward bias, the second one is reverse bias, and that the current flow is really labeling the conventional current flow. But in an NPN transistor, it's really related to the flow of the electrons. In a PNP transistor, that's not the case, because in a PNP transistor, the main charge carrier that flows through the transistor will be holes. So in that case, the hole current is going to follow the conventional current, and that's shown up here in this circuit diagram. There's two main figures of merit, or two figures of merit for bipolar transistors that we need to define. The first one is the common base DC current gain, which is more widely known as alpha. And that's the ratio of the collector current coming out of the end of the transistor compared with the emitter current at the start, where the voltage is applied to the emitter base diode. And we want that to be as high as possible, because it means that most of the current that's gone through the emitter has come out of the collector. So for an NPN transistor, it would be the proportion of electrons which have been able to cross the base and then be collected in the collector. So it's a measure of the bipolar junction transistor's efficiency. So ideally, we want that to be equal to 1, or at least as high as possible. It shows most of the electrons have been swept through the base and made it out to the collector. The common emitter DC current gain is known as beta, and it can be much higher than this now with the advanced types of bipolar transistors. And here, this is a ratio of the collector current to the base current in forward active mode. So what we need to remember is that the collector current is equal to beta times the base current. And so what we need to do with our devices is to try to maximize both alpha and beta to get higher performance, for example, in analog electronics. And we're going to find out through our analysis of the operation of these transistors that to do this, what we need to do is to really optimize the ratio of the doping level in the emitter compared with the base. So I've mentioned already that the emitter has got a higher doping than the collector, but it's also very importantly got a higher doping level compared with the base. We also need to think about the area of the junctions of these transistors. And what you see is that, or what you will see in realistic transistors, is that this first junction has a much smaller area compared with the second junction. And this is all about the optimizing or maximizing the ability of the collector to trap and collect these electrons that are flowing through from that first junction. So we want all of the electrons coming from the emitter to be trapped in the collector. And to do that, we need a very large junction there. So the second thing we need to optimize is the area. So the first thing is the doping. The second thing is the area of the junctions. And the third thing is the width of the base that we tend to call capital W. Again, the thinner the base, you can see if we go back to this schematic, the thinner this base, we call it W, the more likely it is that the electrons that are coming from the emitter or being emitted are going to make it through to the collector. And remember, that's going to maximize the current gain, alpha. So those three parameters are very important, and that's what we're going to be looking at in the next video. This schematic shows the same structure. In fact, this is a PNP, so I don't want to talk about it too much. It's showing the different electron and hole flows through the transistor while it's operating. But because we're not dealing with PNPs, for us it's simpler to look at NPNs and think about the current, the electron flow being in the opposite direction to the conventional current flow. But what is worth pointing out is, despite this being a PNP for the emitter, base and collector, is that just notice these depletion regions which are going to exist between the emitter and base region and the base and collector region. Because whether it's PNP or NPN, we tend to have, or when forward active, we're going to have this first junction here being forward biased, and this second junction here between the base and collector being reverse biased. And you'll remember from our previous notes that because it's forward biased, it's got a smaller depletion region, and because this second one is reverse biased, it's got a larger depletion region. So in one case, the forward biased junction is going to be shrunk, if you remember, so that the carriers can easily get across. The second junction is going to be larger, and that's intentional because we want the electrons to come through from the base to the collector quickly. I have to remind you, as this diagram I think does make, one thing it does do is make clear that both of the charge carriers are important here, and this is unlike the MOS transistor where we're really looking, or the MOSFET I should say, where we're really looking at one type of carrier being important for the collector, for the output characteristics. Here in the bipolar transistor, both types of charge carrier are important, both the electron and hole flow. This is simply an example showing you what effect the spread of gains can have when you're trying to design devices, because remember there's billions of these transistors on a single chip. We try and fabricate them such that they all operate in a similar way, giving the same output current for a given voltage or switch, and that way we can have devices that function as we expect. But we've mentioned two of the sort of key figures of merit or gains, and this is really looking at which one is the most important to monitor in order to control the performance. So in this example, this is the example here, we've got a batch of transistors whereby alpha, which is the ratio of the collector to emitter currents, if you remember that's the common base gain, is very tightly controlled. It appears to be very tightly controlled with a value of 0.995 plus or minus 0.2%. And the question is then, what's the corresponding spread in the value of beta, which is the common emitter gain? So if we write down what these ratios are for alpha and beta, and importantly, we need to remember, as we will show, that the emitter current, i.e., is the sum of the collector current and the base current. Now, in the emitter, which is the first terminal, I suppose, of this transistor, we've got a combination of electron and hole flow. The electrons in an NPN are then going to go through the device and become the collector current, whereas the holes are going to make up the majority of the base current, which we call IB. That's what this is saying here, and we're going to show that operation shortly. If you divide, so the emitter current is the combination of the collector and base currents. If we divide through that expression by IC, we get to something like this, which we can rearrange, and you get 1 over alpha is equal to 1 over beta. Some further rearrangement, and you can show that you get beta as a function of alpha over 1 minus alpha to be precise. And so for your maximum value of alpha, which is 0.995 plus minus plus 0.2%, you get a beta value of 331. These don't have units, they're just ratios. However, for your minimum value of alpha, you're going to get beta of 142. So that's a massive variation, despite alpha appearing to be very well controlled at 0.995, within 0.995. In fact, the spread in your common emitter gain is still going to be very significant, which is going to be problematic when you are trying to do device design. So really, we don't need to be monitoring alpha. What we really need to be looking at is beta. Remember, beta is the ratio of the collector current, the output current, over the base current. So what we want to do is to minimize this value here of the base current and maximize this value here of the collector current. Now remember, to do that, we're going to be looking at NPN transistors. In that case, the collector current at the top is going to be made out of electrons primarily. The base current will consist of hole current mainly, but if you want to look at the PNP transistors, it's the same principle. But in that case, the collector current would be made of holes and the base current would be made of electrons. But because NPNs are generally better, we're going to really concentrate on this type of transistor for the rest of the sections.